Good afternoon, one and all. So sorry for the delay. So today we're going to study about the classic problems of synchronization. So in the last class we studied so what is synchronization, so what is semaphore, and a few other topics. So we understood what is semaphore. So in that we studied what is binary semaphore we studied, and how to use this mutex locks under the binary semaphore that we understood. Then after that, we studied the critical section problem using binary semaphore. Okay, so what is this critical section problem? So as I explained, so we'll be having a four different sections in the critical section problem. Uh, Entry section will be there, then the critical section will be there, then the remainder section and exit section. So how to use our critical section problem, and how to use our semaphores so in solving the critical section problem. So that we studied, okay, in our previous class. And then after that we studied semaphore implementation. Okay, so what is the semaphore means? So as I said, the semaphore is nothing but a small variable. Okay, so using this variable, so how we can achieve the synchronization using this variable, and how we can use this variable for solving the different problems of our synchronization. Okay, so that is what so these are some of the methods. Okay, so what we use in our operating system, so to understand the different uh, process, to understand the different what synchronization methods or techniques, to understand how the operating system handles the process synchronization, how the operating system handles the process scheduling, and how the operating system handles the critical section problem. Okay, so all these are some of the methods so which is used inside the operating system. So then after that we studied so very little bit about the deadlock and starvation. Okay, so this is also one of the different scenario. Okay, as like our problem, so in our operating system, like a process synchronization and critical section problem. Similarly, we have a deadlock and starvation situation. What is this a deadlock situation means? So it is very little bit given here. Okay, so in detail we'll study in the coming classes. So deadlock is a situation where so the two process will be there. So and the process will be holding one resource and it is requesting for the other resource. So which is already used by the next process. If suppose example, if I take the process P naught and the process P1, so P naught is holding one resource and it is waiting for one more, it's waiting for one more resource. It's requesting for one more resource. Whereas, so P1 also is holding the one resource and it is requesting for one more resource. So like this, so we get a situation, so where, so the process, it can't release the resource, but still it is requesting for one more resource. But it is not correct. So until unless it releases any of the resource, okay, so it should not request for the new resource. That is the procedure followed so in the synchronization. Okay, so if this is the case, then we get a situation. Okay, we can't say in all the different cases we'll get the deadlock situation, but most of the cases, okay, so because of this, okay, so we get a deadlock situation. Okay, so how to come out of this deadlock situation and how to solve the deadlocks. Okay, so what is the deadlock prevention? Okay, what is the different methods used for preventing a deadlock? So all this thing we'll discuss in the coming classes. Okay, so that is what we discussed. Then after that we started the new topic that is called as the classic problems of synchronization. So as you can see here, the classic problems of synchronization means, so it is some of the benchmark problems which are available. It is one of the, it is some of the benchmark problems which are available. Okay, so in our synchronization, and we call it as a classic problems of synchronization. And why it is called as a classic problems of synchronization means, so because so whenever you design, okay, so whenever you design any kind of a new method or a new technique or a new algorithm, that algorithm or a method need to be tested with these classic problems of synchronization. What are the classic problems of synchronization? We have a bound buffer problem is there, and we have a reader writer problem is there, and we have this dining philosopher problem is there. All these three are for our syllabus. So under classic problems of synchronization. Okay, so if my algorithm, if my method, if my technique, so which I want to use for our process synchronization, if it is holds good for these three problems, then I can say my algorithm is perfect. Okay, it is a very good algorithm what I designed. Okay, so that is the meaning. So we have this bound buffer problem. The bound buffer problem, as we discussed, is related to the producer consumer problem. Okay, so a bound buffer problem is nothing but a producer and consumer problem. Okay, so where we studied this producer consumer problem, so we studied producer and a consumer problem in our synchronization. Okay, so if I want to synchronize something, if I want to synchronize something, then I want to design an algorithm. Okay, that algorithm has to be tested with producer and a consumer problem. Okay, so if the algorithm holds good for this producer and a consumer problem, then I can use that algorithm in my process synchronization. Okay, so that is what we studied in the producer consumer problem. So bound buffer problem is nothing but it is a producer consumer problem only. So where we use some procedure like producer procedure is there and consumer procedure is there, and also we use some of the variables like semaphores like mutex is one semaphore is there, then empty is a one more semaphore, and full is a one more semaphore. These are some three different variables. Semaphore nothing but, as I said, it is just a simple variable. Okay, using this variable, so we try to write a program logic in such a way that, okay, so we achieve the synchronization. Okay, so here, so we have some variables like integer n, semaphore mutex, semaphore empty, semaphore full is there. So with that, we have a procedure for producer, and where there is a procedure for a consumer also, and we call internally some functions like wait function is there and signal function is there. To wait and a signal, we pass some variables. We pass these semaphores at a proper time. Okay, at a proper time, so that there won't be any kind of a problem. Okay, there won't be any kind of a problem, and automatically, so the process will get synchronized. Okay, so that is how, so we maintain, or that is how we use our producer consumer problem code, okay, to achieve the synchronization. Okay, so then after that, so we go for the next kind of a problem that is called as a reader writer problem. Okay, so it is very similar to your producer consumer problem, so which is called as a readers and writer problem. Okay, two terms are there, one is a reader and a writer. Okay, so as you can see here, so to the database, if I want to read something from the database, so you can perform only read operation. If I want to write something onto a database, we can perform only write operation. So both the operation I can't perform. Both the read operation and the write operation, both operation I can't perform at the same time. At any given time, at any given time interval, I can't perform both the operation together. That is reading and writing. It is not possible at all. Okay, so it should be properly synchronized. If I'm reading, okay, so I should not write. If I'm writing, I should not read. Okay, so this is meaning of the synchronization. Okay, so what is this reader and writer problem? The data set is shared among number of concurrent process. Okay, so of course this we know that the data set or our database, it is shared among the n number of process. When n number of process using a centralized data, when n number of process, when it is using a centralized data, so we can't expect, okay, the process to follow the synchronization. Okay, we can't expect, it's very difficult. So because of that, we should come out with some kind of a strategy or an algorithm, so that all the process which want to use this data, centralized data, they should be in a proper synchronous order. Okay, so they should work in a proper synchronous order. Okay, so if they want to read, okay, let them read synchronously. If they want to write, okay, let them write synchronously. If they want to perform read and write, okay, let them do both read and write synchronously, so without any overlap. Okay, there should not be any overlapping. Okay, so that we should keep in mind. So that is called as the reader and the writer problem. What is this reader means? Readers are process which want to only read the database. As you can see here, read the database. So reader, so which performs only reading of a database content, that is called reader. And writer are the process which want to update the database. which want to update the database, that is read and write. Okay, they want to update the database. So when we have this kind of a process, one is a write process is there, one more is a read process is there. When both the process, a read and write process, they want to perform, okay, some operation on the centralized database, then so they should perform in a synchronous order. So that is the condition here. So obviously if two readers can access the shared database simultaneously without any problem. If there are two readers are there, they can access the database simultaneously without any problem. However, if a writer and other process access the shared database simultaneously, then problem may arise. Okay, if there is a writer is there and if there is a reader is there. Okay, so when they want to access the database simultaneously, so that time we may get some problem. Okay, so why that problem? Because so somebody want to write something onto the database and somebody want to read from the database. Okay, so if there is no any communication among themselves, okay, and they're performing reading and writing both at the same time, so that time, okay, automatically it's very very difficult, okay, so to handle this situation, and we get into some kind of a problem, some kind of a trouble. Okay, so what is the solution? Okay, so this is our problem. Okay, so this is our problem, and let us see the solution. What is the solution? Solution is a writer must have exclusive access to the shared database while writing onto the while writing to the database. Okay, so writer must have exclusive access. Writer must have exclusive access to the shared database while writing onto a database. Okay, so means what? So the writer should have exclusive access, dedicated access to the database when it want to write, when he want to write something onto database. Okay, so if a reader want to have a same thing, okay, applies for the reader also. The reader want to read something from the database. Okay, he should have some exclusive access to the database. So when you want to perform the reading, okay, so that is called as the solution. Okay, that solution we can give for reader and writer problem. Means what? Okay, in a simple words, if any one person is reading, okay, so let him read. Okay, so we should not allow the writing person. Okay, so if any one person want to write, let him write. Okay, we should not allow the reading. Okay, so this is how, so we should use our reader writer problem. Okay, and we should achieve the synchronization. So what are the different shared data? So in the reader writer problem, so there are shared data like mutex is there. So there are shared data like WRT. Okay, this is one more semaphore. Then read count is there. Read count is there. Then WRT is there. Okay, all these are some of the variables or some of the semaphores. Semaphore nothing but a variable. Okay, semaphores which we are using. So in the reader writer problem. Okay, so then after that, initialization. Okay, what is this initialization means? So initialization, we assign some value for this variables. So mutex is equal to 1, wrt is equal to 1, and read count is equal to 1. Okay, so that some small values, okay, some initial values we are assigned to all these three variables. Then we write our write procedure, then we write our read procedure. Using this read and write procedure, so we perform reading and writing synchronously. Okay, and we use this inbuilt function like wait function is there. Then after that signal function is there. Then again the signal function, again the wait function. Okay, so all this wait and a signal function we use in the read and write procedure, and we design our read and write procedure so that with the help of these three variables, mutex, wrt, and a read count, and with the help of two functions, that is a wait and a signal function, so we try to achieve the synchronization. So and we try to get the result for reader writer problem. So and we see that, okay, so the reader writer problem is in a synchronous order. Okay, so that is how we use our reader writer problem. Okay, so this is also one of the classic problems of synchronization. The reader writer problem and its solution are used to provide reader writer locks. Okay, so lock is also a one kind of a variable. Okay, the mode of lock need to be specified. Okay, the mode of lock using is need to be specified. One is a read mode is there, other is a write mode is there. Okay, one is a read mode, other is a write mode is there. A multiple process are permitted to concurrently acquire the lock in the read mode. These logs are most useful for following situations. Okay, so in different situation we can use these logs. So what are the situation where we are using this log? In application where it is easy to identify, in applications where it is easy to identify, in application that have more readers than writers. Okay, so in application where we have more readers than writers, there we can use our log kind of a system. Okay, so that is one of the important thing about reader writer logs. Okay, so but what we need to understand here, the reader writer problem is also a classic problems of synchronization, where so we can achieve the synchronization. Okay, so using this reader writer problem, and we can design our algorithm. Okay, so which works for reader writer problem, so then we can use that algorithm inside the operating system. Okay, so then we go for the next problem. This is a next classic problems of synchronization, that is called as a dining philosopher problem. What is this dining philosopher problem means? The problem statement of dining philosopher problem. Okay, what is the problem statement? There are five philosophers at five chopsticks. Okay, there are five philosophers. Okay, who are sitting around the dining table with the five chopsticks. Okay, chopsticks is nothing but the stick which the Chinese people use. Okay, for eating a food. Okay, so that is a chopstick. Okay, so they are using. Then after that, a philosopher is either eating with two chopsticks or thinking. Okay, so that is a problem definition, where the philosopher maybe you may be using the chopstick for eating, or you may be simply holding a chopstick and you may be thinking. The philosopher share a circular table. The table has a bowl of rice in center and five single chopsticks. Okay, so this is how. So we have some problem statement given. For time to time, a philosopher gets angry and tries to pick up two chopsticks at the closest to her. A philosopher may pick up only one chopstick at a time. Obviously, she cannot pick up the chopstick at this already in the hand of a neighbor. So all these are the problem which is given in the diagram. We can explain. Okay, so this is the table where five philosophers are sitting here. One, two, three, four, and a five. Okay, so all the five philosophers, they are having a chopstick. Okay, they are having a chopstick. This philosopher having a chopstick here, chopstick here, chopstick here, chopstick here. Okay, and this philosopher having a one more chopstick. So like this, there are the five chopsticks are there, and there is a bowl of rice. Okay, so they want to eat that rice, bowl of rice. Okay, which is placed at the center of the table. Okay, if that is a scenario given, but with only one chopstick. Okay, so we can't eat the food. We can't use the rice. Okay, we can't eat the rice. Okay, with the help of the two chopsticks only, we can eat the rice. Okay, if that is a scenario given, if that is a problem given, so how to solve this kind of a problem? Okay, so that the all the five philosophers, they work in simultaneously, synchronously, so that all the five people eat the rice with the help of the two chopsticks. With the help of the two chopsticks. Okay, at any given point of a time, so they should use only two chopsticks for eating a food, eating a rice. But how to do it? Okay, how to do it, and how to write a code. Okay, so how to solve this problem? Okay, so then, so if that is a problem given, so what is the shared data here? We should identify the shared data. The semaphore chopsticks is the shared data. We have five chopsticks here. Okay, as you can see here, we have a five chopstick here, so which is called as shared data. And initialized chopsticks, so 5 is equal to 1. So because, so we have only one chopsticks which is assigned, which is initialized to each and every philosopher. Okay, so one philosopher, he can have only one chopstick at any given point of a time. But you should make okay, you should make use of other chopstick of the next philosopher who is sitting to the left or right of the philosopher, present philosopher, and you should use the two chopsticks for eating a rice, which is kept at the center of the table. Okay, so for that, we should write a proper program. We should write a proper code, so that we can make the philosophers to eat the rice. Okay, so without any kind of a problem, without any with a proper synchronization. So for that, so this is a small code given. The situation of the dining philosopher problem, it is shown in the diagram. The structure of the philosophers, okay, it is shown in this small diagram. Then after that, Okay, so if I go here, the disadvantages. Okay, what is the disadvantage of this problem? So deadlock may occur if five philosophers become hungry simultaneously and grab their left chopstick. Okay, so what do you mean by that? Okay, so always the one chopstick will be available with each and every philosopher. So when they all become hungry, automatically they grab that one chopstick. Okay, so which is kept at the left side of the philosopher. So that is common. Okay, so they wait for the other chopstick. Okay, they wait for the other chopstick because without the two chopsticks they can't have their food. Okay, they can't eat the rice. So because of that, they wait for they wait for the rice. Okay, sorry, they wait for the one more chopstick to have their food, to eat the food. Okay, so because of that, so they may get into some kind of a situation that is called a deadlock situation. When each philosopher tries to grab the right chopstick, she will delayed forever. So because, so whenever the left chopstick is there with the one philosopher, automatically he will try to grab the right chopstick which is already there in the one more with the one more philosopher. So he can't take that one more chopstick for eating a food, okay, or eating a rice. Okay, that is not possible. So because, so already it is taken up by the one more philosopher. So this creates a deadlock situation, and this creates the delay forever. Okay, so this creates the delay forever. So because they can't get, okay, the philosopher, he won't get the right chopstick at all for eating the food or eating a rice. Okay, so this scenario is called as a deadlock situation. Three possible remedies for deadlock problem. So this is called remedies. Okay, so three possible remedies for the deadlock problem. What are the three possible remedies? First one, allow at most four philosophers to sitting simultaneously at the table. Okay, instead of making the five professors or five philosophers to sit onto the table, so let us allow four philosophers. Okay, let us allow four philosophers to sit on the table, so that one additional chopstick will be there. The chopsticks remain the same. The number of chopsticks is five only. But instead of making the five people to sit on the table, we're making the four people to sit on the table, so that whatever the additional chopstick which is available, that is chopstick is shared among all the four, so that simultaneously, if they use continuously, or if they use synchronously the one extra additional chopstick which is available, automatically, so they can finish off their food. Okay, they can eat the rice. Okay, so that is the first remedies for the deadlock. Second one, allow the philosopher to pick up the chopstick only if both the chopsticks are available. Okay, so allow the philosopher to pick up the chopstick, so when both the chopsticks are available. Okay, so that situation, when we get that situation, when, so we make only four professors or four philosophers to sit on the table, so with the five chopsticks. So that time, so one philosopher will be allowed to pick the right chopsticks. Already you'll be having a left chopstick, and he is able to pick the right chopstick also, so that he can eat the rice which is kept on the table. Okay, so that is the one more solution or remedy we can give. And the last one is called as the use a asymmetric solution. Okay, use a asymmetric solution, that is an odd philosopher pick the first her left chopstick and then right chopstick. Okay, so use some kind of a asymmetric solution, so where odd philosopher, okay, odd philosopher means he may be one, he may be three, he may be five. Okay, odd philosopher, let him pick the first her left chopstick then the right chopstick. Okay, so that is the one more solution we can provide. Okay, so which is called as the remedies to the deadlock situation, because of a limited number of chopstick. Okay, so with the philosophers. Okay, so that is the last solution or last remedy for the deadlock situation. Okay, so that is about the classic problems of synchronization. So we have these three main classic problems of synchronization. So one is our bounded buffer problem. The one is a reader writer problem, and last one is called as a dining philosopher problem. Okay, so these three are called as the classic problems of synchronization. And as I said, so these are called as classic problems of synchronization, because so if my algorithm, if my method, if my strategy, okay, so if it works for these classic problems of synchronization, if it works for this benchmark problems of synchronization, so then automatically we can use that algorithm, we can use that method. So in the synchronization solving of the operating system. So because of that, so whatever the method you propose, okay, so automatically that is tested with this classic problems of synchronization. So one is bound buffer problem. If it is working fine for the bound buffer problem, so then okay. So if it is working fine from reader writer problem, then it is okay. If it is working fine for dynamic philosopher problem, so then we can say the algorithm or a methodology which you want to implement, so it is correct. Okay, then that can be used with the operating system. Okay, so then so we go for the next one. So that is called as the monitors. Okay, so what is this monitor means? Okay, so this is one of the different concept, as like your semaphore, as like your critical section, as like your what the synchronization problem. Okay, monitor is what is this monitor means? So let us understand what is a monitor. So monitor is a high level synchronization construct. Okay, so please understand here, it is a high level synchronization construct. Okay, what is this construct means? Okay, so please see here. So construct is nothing but so we are creating a data type. We are creating a class kind of a structure. So which is a high level construct. So means what? So this construct we design in the high level language like our C++ language, like our Java language. Okay, using this high level construct, using this high level language, so we design a class. Okay, so which is called as a monitor. Okay, so that is why it's called as a high level synchronization. Why we design this monitor? So to achieve the synchronization, so we design the monitors. Okay, so that is a high level construct. It provides a conventional and efficient effective mechanism for process synchronization. Okay, so please understand here. So it provides a conventional and effective mechanism for process synchronization. So our main aim is to see that the process is synchronized. What is the conventional mechanism? What is the effective mechanism for process synchronization? So that can be achieved using the monitors. Okay, so nothing but we are creating a class instead of creating a simple semaphore like semaphore X, semaphore Y, semaphore mutex, semaphore lock and all. So instead of that, so we are creating the whole class itself, so that so it becomes a conventional way of effective process synchronization method. Okay, so next one, the needs for the monitor. Okay, what are the needs of the monitor? So when the program use a semaphore incorrectly, following types of error may occur. Okay, so whenever the program uses the presently available semaphores or variables incorrectly, we can expect some kind of a problems. We can expect some kind of a errors. We can expect some kind of a issues to occur. Okay, so what are the issues? What are the problems we come across? So before we use this monitor, before you go for monitors, let us understand. The first problem is suppose that a process interchanges the order in which the wait and signal operations on the semaphore are execute, resulting in the following execution. Okay, so suppose the process. Okay, so we have two already readily available functions. One is a wait function is there, other is a signal function is there. Okay, using this wait and signal function properly, okay, we are able to achieve, okay, the process synchronization with the help of the semaphore. So it should be in a order. Okay, the wait and signal function, whatever is there, it should be in a order. If the order is mismatching, okay, if there is no order, if the order is mismatching, then that time automatically what happens? Okay, it will leads to some kind of a problem called as the synchronization problem. Okay, so that may be the one of the situation where so we get the synchronization problem even though we are using a semaphore, even though we are using a wait and a signal function. So what is the second scenario? What is the second situation? Suppose that a process replace the signal mutex with the wait mutex, that is executes like this. Okay, so whenever the process replaces the signal mutex with the wait mutex nothing but the variable, so which especially we use for our signal and which we specially use for our wait function. Okay, so the respective variable has to be passed to the wait and a signal function. If there is an interchange between the variables of the signal function, if the signal function, if there is an interchange between the variables of the wait function, automatically it leads to another kind of a problem. Okay, so the one more problem we come across is suppose that the process omits the wait function. okay, or signal function, or both function, then it leads to one more difficult situation. Suppose we are using both weight and a signal function. So due to some problem, okay, so while writing the program, the if the programmer, okay, if he omits the weight function, okay, and if he omits the signal function, so that time, okay, it leads to one more kind of a situation, or one more kind of a problem. So that which leads to the what a process synchronization problem. So because of that, so we should see that all these problems are solved, so with the help of the monitors. Okay, so this is how, so we use our a monitor, a monitor uh, which is a high level synchronization construct. Okay, so with the help of this high level synchronization construct, so we can achieve, okay, so we can achieve the synchronous in a proper order, so without any kind of a problem, even though there is a mismatch, even though there is a mismatch in the variable passing to the weight and a signal, even though there is a interchange between the weight and a signal function, even though uh, there is a omission of a weight function, or a omission of a signal function. Okay, so all these problems can be solved with the very efficient high level synchronization construct that is called as a monitors. Okay, so we'll see this monitors in detail in the next class, and the monitors usage in the next class. Okay, so thank you for listening. Thank you.